In 4.5, there are two main concepts that you need to understand really well, and those are the concepts of differentials, which this lesson, this video will be on, and that of a tangent line approximation or a linearization, a linear approximation. That we will cover in our next video. Both of those are in 4-5 of our book, and they're both very popular uses of the derivative. So a differential is when you focus on one part of the rate of change at a time. So it has to begin with our understanding of what a derivative is. And so I need you to recall that when you see this expression, dy dx, that the meaning of that was the derivative, the change in y over the change in x at that instant where the change is happening. So this is sort of like instantaneous change in y over instantaneous change in x. Because if you recall, the definition of f prime is when you're taking a limit as h, which refers to the change in x. As the change in x approaches 0, of f of x plus h minus f of x all over h. So right when h hits 0, like right at that instant, I have 0 over 0, which we're not algebraically able to determine what that equals. This notion of the limit is what helped us actually calculate what that 0 over 0 equals, what that instantaneous rate of change equals. And once we find that out, we end up with our dy dx. So that's our instantaneous change in y over our instantaneous change in x. Now a differential is when you, instead of thinking of it as dy dx, you break these into their separate pieces. And we just look at one aspect of the rate of change. So dy could be seen as the instantaneous change in y, and dx is seen as the instantaneous change in x. And then we could, in a sense, multiply dx to both sides, causing it to cancel here and then appear on this side. And so we could think of the instantaneous change in y as being equal to the derivative of f, the rate of change, the dy dx, times the instantaneous change in x. And then this allows us to find just the change in y. Forget about change in y over change in x, just the change in y given a change in x. I'll start with a more abstract example, one that has no real-world application, but it will give us the practice of splitting this up. So here they give us an equation for y. So this is my f of x, this expression here. And I'm being asked to just find the dy. And so I have to remember that that's simply equal to the derivative of the function at x times the instantaneous change in x. So I'm going to go ahead and find the derivative of this, which will require using quotient rule. So u would be 2x, v would be 1 plus x squared, u prime would be 2, and v prime would be 2x. So then my f prime of x would be u prime v minus v prime u, all over v squared. And then simplifying, we get 2 plus 2x squared minus 4x squared all over the quantity 1 plus x squared squared. Further simplifying leads to 2 minus 2x squared all over 1 plus x squared squared. So dy, to answer part A, is equal to this expression times dx. And that right there would be our answer to part A. So instead of writing it this way, which we do when we're just looking for the rate of change, if we're just looking for the rate of change, we would think of this as equaling dy dx. We would say, okay, dy dx is equal to the derivative. So it's really not saying anything different than this. It's just focusing in only on the dy. And so it's kind of like the dx, in a sense, has just been multiplied to both sides. We don't like to think of it that way, but in a sense that's what's happening. Is it's like dy dx times dx causes the dx's to cancel, and so then dy is just equal to the derivative times dx. Now let me show you in this part B why that could be useful. So let's say I knew that my change in x was 0.1. So I'm moving just 0.1 either to the right or left of this x value, -2. I could find the resulting change in y. And so I'm going to use this expression here to do part B. So I would find that dy would be equal to, and I'm going to plug that value, -2, in for the x, because that's my x value where I'm looking at the change in y at. It's right instantaneously at -2. And I'm shifting either right or left 0.1, and I want to see how that will affect my shift in y. So I'll go ahead and plug in the -2 wherever there's an x. And then I'll multiply this expression by dx, which is 0.1. And then that will give me, in effect, my dy. So I just need to simplify this a little bit. So the numerator ends up being -6. The denominator ends up being 25. I'm multiplying all that by 0.1. This fraction here ends up being -0.24. And I'm multiplying that by 0.1, so I just moved the decimal one more place to the left. So my dy, if you could follow me this way, is equal to -0.04. Excuse me, -0.024. So if I were to slide right or left 0.1 from this x value, my change in y would go down 0.024. Is kind of what's happening there. To give you maybe a better sense of how this is used, we'll take it to an actual application in example 2. Here we have a radius of a circle increasing. We have a radius changing from 2 meters to 2.02 meters. And now we want to estimate the resulting change in area. And this is an instantaneous rate of change, so we wouldn't want to just recalculate the area. We want to figure out the rate of change of area with respect to radius, and then split that apart to find my differentials, if you will. So I know that the area with respect to the radius of a circle is pi times the radius squared. So I could say that the change in area with respect to the radius, remember pi is just a constant, so this would just be constant multiple rule and the power rule, would just be 2 pi r. So then I could say that my change in area specifically would be 2 pi r times the change in r. Because in a sense, it's like I'm multiplying dr to both sides. Okay. So what I need to figure out is, if I want to find my change in area, I need to figure out my value of r at the instant it was changing, and then my value of dr, how much did it change. So 2, right here, this is my value of r at the instant it changes. So that value is going to be plugged in for r. Then the change in r is the change from the value of r at the instant it changes to what it changed to, which was 2.02. So my dr would be the difference, the change in r. And so it would be 0.02. And that value would get plugged in for the dr. And so I can find now my resulting change in area, my dA, would just be 2 pi times 2 times 0.02. And so that would just turn into, this would be 4 times 0.02, which would be 0.08 pi. And since the radius was measured in meters, and this is the area, it would be meters squared. Because right here, that's 2 meters, and right here is 0.02 meters. So meters times meters, we get meters squared. And that's how much the area changed when the radius changed by 0.02 meters. Now, if we wanted to estimate as a percentage of the original area, we go back and we find what the original area was. We figure out what the area was when the radius was 2, and that area was 4 pi. This is how much the area changed. So I just want to figure out what this is as a percent of the original area, so I just simply divide. The change, 0.08 pi, over the original. So that's change in area divided by the original area. So we'll figure out what that is. Turns out that is 0.02 because the pi's cancel, and then 8 divided by 4 is 2, and there were 2 decimal places. And since we're looking at percents, that would be equivalent to 2%. So you could say that the area changed by 2% of its original amount. In example 3, we see another very commonly used application of differentials, which is, in this scenario, we're measuring some things. We're measuring the edge of a cube in this particular case. And we can see that it was measured, or we're going to allow ourselves to measure with a little bit of error, maybe up to 1% of error. And we want to see how that error would affect our volume calculation. So this error could be seen as the change in the length of the side. So maybe we could call that ds. And we want to figure out dv. So what's happening here is we're measuring the edge of a cube. So the volume of a cube would just be side cubed because all 3 dimensions are equivalent. So it's basically like you have 6 squares being put together, and they all have, each dimension has the length s. So the volume would just be the area of the base, which is s squared, times the height, which is s. So then you get s to the 3rd. Okay, now the change in volume with respect to the side would be 3s squared. That's the change in volume with respect to the side. So then you could think of the change in volume as just being 3s squared times the change in the side. All right, now we need to figure out again the value of s at the instant it's changing and the value of that change. Okay, so we measured this cube to be 10 centimeters, so that could be considered the value of s at the instant it's changing. And we are allowing, allowing ourselves to have up to an error of 1%, either for better or for worse, so 1% over or 1% under. So that's going to be our change in s, will be the 1% of our side. So my ds measurement is going to be 1% of 10, or 0.01 times 10. And so in that case, I get 0.1. So my change in s, the length of the side, is going to be off by 0.1 centimeters. So now I can figure out how this error of 0.1 centimeters is going to affect the error in my volume calculation. So my volume calculation is now 3 times 10 squared times 0.1. And so that ends up being 300 times 0.1, which moves the decimal 1 spot back. So that ends up being 30 cubic centimeters. So my error of 1% with the side ends up creating an error of about 30 cubic centimeters for the volume inside the box. But it wants us to write our answer as a percentage of the volume calculation. So we would find what our volume would be if the side was actually 10. And that would just be 1,000 cubic centimeters. And if we're off by 0.1, then our volume calculation will be off by 30. So to figure out the percent, we'd take our change over our actual, and that just gives us 3 over 100, which is 3%. So our calculation for the volume would end up being off by 3% if the calculation of our side was off by 1%. So we'll have a 3% error in volume calculation. And so that's another common application of differentials. The other and final application of differentials is allowing ourselves to have up to some error. We can allow some error in measurement typically there is, because just with human error in measuring things, but certain amounts of error can be tolerated. So this is telling us that the volume is to be calculated with an error of no more than 1% of the true value. So we're allowed to have an error of up to 1% of the true value. So now we need to figure out, okay, well, what's the greatest error that can be tolerated in the measurement of h? Well, I don't know if you want to take a guess here. I'm just going to take a guess, because if you notice before, when our side of the cube was allowed to have an error of 1, my volume then had an error of 3, which is interesting to me because the side has 1 dimension and the volume has 3 dimensions. 1, 2, 3. And the error in volume ended up being 3 times the error in that first dimension of the edge. So I don't know if this will come out to that, but I think it'd be interesting if my change in height, or my error in height, was a third of this, basically, because this would have to be 3 times my change in height. So just something to keep in mind while we go. Okay, so, oh, and also the height and radius of the right circular cylinder are equal, which helps because that gives us only one variable. So then the volume, because typically volume is equal to pi r squared h, but this is telling me that h equals r. So then I can just substitute my r squared with h squared and get a formula for volume in terms of just h, which is helpful because now I only have one variable. So what that tells me is that my change in volume with respect to height would be 3 pi h squared. And then that tells me that my change in volume specifically would be 3 pi h squared times my change in height. Alright, now notice that my change in volume can be no more than, so that means it has to be less than or equal to 1% of the true value. So 0.01 times the true value, which would be v, would just be this, or this with respect to h. So I'm going to come over to this expression here, and I'm going to say that dv, which is equal to 3 pi h squared dh, has to stay less than or equal to 0.01 times the true value, v. And then I'm going to use this expression for v, so I can get things in terms of h here, because I need to ultimately find what dh is. So I'm going to say that 3 pi h squared dh has to stay less than or equal to 0.01 times the true value, which is pi h cubed. And then I'm going to solve for dh. And so I'm going to divide basically by 3 pi h squared to get my dh alone. So then the measurement in height, the change in height, can be no more than, let's see, the pi's are going to cancel, and then these h's will cancel, leaving me with 1 h, so I'm going to end up with 0.01 h over 3. And if I divide this, 0.01 over 3, that ends up being 0.003333, 3 repeating h. And so if I change that into a percent, it would be 0.3 repeating percent, or 1/3 percent. So you could say then that the measurement, or the error, excuse me, this is the error in measurement. The error in measurement of the height has to stay less than or equal to 0.3% of the original height, or it can be no more than 1/3% of the original height h. And that's differentials for you, so I'll see you in class and we will attempt to find all kinds of changes and things together. See you there.